Hi everyone, and welcome back to another one of these physics videos. So as you can see, we're going to be talking about rotating collars today. And essentially I have this whole setup right here, and essentially it's just a pipe that's rotating at omega, and then there's a elbow joint attached to it, and then attached to this elbow joint is another pipe, basically causing it to have an angle theta. And then on this pipe we have this collar, and essentially we're going to be focusing just on this collar this whole time, and then essentially since it's spinning around, this spring is holding this collar in place. So, and basically to give you a better idea of the motion, basically the collar is going to be spinning around like this, So it's going to be spinning like this, just like omega's like that, and then it's going to have basically an inward acceleration then in the end. So anyways, so basically what we're going to be doing with this whole problem is we're going to basically find out what omega is. So, and we're going to start off finding out what omega is without any friction. So essentially when we start out, we're going to ignore the coefficient of static friction, We're going to ignore that. And then afterwards, we're going to involve it, and we're basically going to get a range for omega to be in for these lengths and all the parameters involved. So anyways, so in order to start out, we're going to start off by breaking up these forces into components. So as you can see, I didn't draw the friction force just yet, just because it's we're not involving it the first problem. So, and another thing to point out, and you're probably think this to yourself also, is you're like, let's tilt our axes, which would make sense sort of, just because the normal direction is in the y direction then, and then your force is in the x direction. But you know what, don't. I'm just going to tell you now, don't. And basically, if you saw in the last video, it was a crate and ramp problem. Whenever you see the word ramp in a problem, or you just have a picture with a ramp and that's the problem, just whenever ramp comes up, you're going to want to tilt your axes. Whenever ramp doesn't come up, do it normally. That's the key to tilting your axes. When you hear the word ramp, tilt your axes. When you don't hear the word ramp, don't tilt your axes. It's as simple as that, I feel like. But you do kind of have to analyze the whole situation, and I'll show you why you kind of have to tilt your axes. So as you saw earlier, I said the acceleration is going to be like in the x direction. It's going to be completely inward right here. And so essentially, when we don't tilt our axes, we have x, and basically we're going to be accelerating in the x direction. So x is going to be dynamic, while y is static. And if we tilted our axes, then both would be dynamic. It would just be a lot harder to, it would be a bigger mess to deal with problem-wise, and having to do the sum of the forces. So don't tilt your axes, leave them like this, That's perfectly good. It's even, it's great, in my opinion. So anyway, so if we're going to start off this problem, we got to, like I said, break up these guys into components. So if we break up this guy into components, we have our y component, and then our x component, and then we also have our y component for our spring force, our x component, and then our y component. And then so basically this is going to be theta in the end, and you can just see that just because, like, if you make a line, this angle is going to be theta, and that's basically this line right here. So it's the horizontal line. Now with this angle, basically in the end, if you draw this normal force right here, break it up into components, like so. If you do the piece of paper method again, put the piece of paper right here, tilt your piece of paper in this direction this many degrees, you'll find out that, the piece of paper moved theta, So in the end, this is going to be theta. And so in the end, you could probably just, say that, this is going to be 90 minus theta, and then so this is going to be theta, You can do it like that, using these right angles right here, I just like the piece of paper method just because it's so straightforward. Like it's hard to mess up. Very, very hard to mess up, at least in my opinion. So, but yeah, so let me get rid of that. So this is theta. So now we have all our vectors split up into components and the angles assigned to them too. So we can actually start solving now, but you're probably thinking to yourself also like, well, we have these thetas, but what is theta? So this is kind of a weird problem, but you're gonna be getting theta from this, or essentially you're not even gonna be getting theta. You're gonna be getting cosine of theta and sine of theta from this. So since this triangle is gonna be like a similar triangle to this triangle, and theta is the same, cosine of theta is gonna be the same value in the end. Cosine of theta is really just a ratio of like the adjacent over the hypotenuse and the opposite over the hypotenuse, opposite or adjacent for tangent, but really it's a ratio in the end, and so it's useful for any kind of triangle. Well, right triangle, of course, but yeah, so essentially then cosine of theta is then going to be just 4 over 5. So, and then sine of theta is going to equal 3 over 5. So essentially wherever we see a cosine, we're going to plug in 4 over 5. Whenever we see a sine, we're going to plug in 3 over 5. Simple as that, or, 0.8 and 0.6. So, but anyway, so now that we have everything broken up into components, let's do the sum of the forces. So if we do the sum of the forces in the y direction, always pick the easiest direction. So that's going to equal 0 because we're not accelerating up and down, we're accelerating to the left. We're accelerating inward. So anyway, so now we're going to have n cosine of theta. So it's positive because it's heading in the positive direction. Then we have minus because it's heading in the negative direction. F, or I'm just going to put in k delta L. So k delta L, and then it's going to be sine of theta, and then minus, or wait, which is mg, because mg is vertical. So essentially we can solve for what n is in this scenario. So really n times by cosine theta, if we add both these to the other side, cosine theta is 4 over 5. This is going to equal basically k delta L. Sine theta is 3 over 5, so it's 3 over 5 minus mg. So then we know that n is then going to equal k delta L. The 5s are going to essentially cancel, and then so you're just going to get 3/4 right here minus mg, which is going to be 5 over 4 then. So that's what n equals, and then so now let's move on and do the sum of the forces in the x direction. So there's almost two ways of going about this, so you could just make your coordinate system like this, a little bit backwards since we're accelerating in this direction, or you could just say it's a negative acceleration, it's heading in the negative direction if you keep it like this. So either way is fine, this way means you don't have to multiply a -1 on both sides. The other way means that you are going to multiply a -1 on both sides. So essentially we're going to be accelerating in this direction, so it's going to be negative ma. So I'm just keeping the standard coordinate system. If you changed it, then this would be positive, but we're just going to make it negative for right now. So, and then we have basically negative, so minus, and so it's going to be sine theta minus k delta L cosine theta. Basically, multiply -1 on both sides, So then we get our acceleration, or you know what, our acceleration is just going to equal r times omega squared, just because we have a centrifugal acceleration, because we're going in a circle. And then r is then going to equal, because this is r, you know, if that's r, and you know, so basically essentially this is r. So it's going to be L cosine of theta. So it's going to be L cosine of theta. So R then equals L 4/5. You know, L, you know, we'll just write 4/5. Keep the fractions. And then, so this is just going to be L 4/5 omega squared. So now if we plug in A into here now, we get M L. Here. Try to salvage that one, but that didn't work out too well. Okay, omega squared, and that's going to equal, so now let's just calculate this number, you know, make it a little bit easier for ourselves, and then we'll plug it into here. But really it's going to be n, then 3/5 plus k delta L 4/5. Here we go. So now let's just calculate what n is real quick. But before I continue, I just have to point out that I found one of my mistakes. When you add this to the other side, and then you also add this to the other side, your weight's going to be positive. So so if you caught that, good for you. Good for you. But yeah, so that's going to be that in the end. And then, because I was wondering why I had a negative normal force, and I was like, that's not right. But anyways, so it's going to be 100 times by, and then we have delta L right here. So it's going to be L minus L naught. So L final minus L initial. You know, whenever you see a delta, it's final minus initial. Always final minus initial. It's never initial minus final. Final minus initial every time. So anyways, really it's this length is just 0.4. It's L is 0.4, but the unstretched length is going to be 0.3. So of the spring. So if you subtract the two, then you get 0.1 meters in the end. So then we're just going to multiply by 0.1 times that by 0.75, because that's 3/4, plus 2 times by 9.81 times by 5/4. So, and then we get 32.025 newtons. So that's what n is, and then we can plug n into here, and then we can essentially solve for what omega is in the end. And omega is just going to be our angular velocity. So now if we calculate what the right side equals, then we're going to get, so it's just ml 4/5 omega squared is going to equal, so it's going to be, so that's what n is, so second answer, times by 0.6 plus 100 times by 0.1, because that's what delta L is, and then times by 0.8. And so that's what the right-hand side equals, so 27.215. 7.215. And then so now we need to just divide by everything, but the omega squared, and then take the square root of it. And then we should have omega no friction. So, and that should be in between our next two values that we get in the end. So anyway, so now we divide this by our mass, which is 2, times by L, which is 0.4, and then times that by 0.8. then close parentheses. So we get that, and then so omega squared equals 42.4. I believe that's what it said, or 0.5. But yeah, we're just gonna take the square root anyway. So second answer. So omega is going to be 6.52 radians per second. So omega, no friction, is going to equal 6.52 rad per second, so radians per second. So then you'd probably convert this to revolutions per minute, but you know, it just radians per second. So usually the problem will give you in revolutions per minute for omega, but you're gonna have to convert that every time. So I don't like revolutions per minute. It's kind of useful, I guess, but kind of not, I guess. You know. Your equations require radians per second. So now that I've officially waved my magic wand and, you know, erased everything, moved things in different spots, you know, we're going to be doing basically finding omega when there's friction involved. So basically what I want to do is find the basically smaller value of omega. So for the smaller value of omega, your friction is going to be going up the pipe, you know, so up the angle. And then, so if we break those up into components, this is going to be theta, and then this is going to just be mu s times by n. So if we max it out, you know, so basically we're getting our smallest angle possible for this, just because in the end, this is going to be in the opposite direction of these two components, and so it's going to basically subtract them compared to if it was on this side, you know, it would be adding the 3, you know, so it's going to take away a little bit from these two x components, which hence why you're going to have a smaller omega in the end. So basically your friction is going up the pipe for this scenario. So now if we do the sum of the forces in the y direction, set it equal to 0, and basically get the same stuff again. We get n cosine of theta. You know, I'm just going to write 4/5, save some space. And then we're going to have minus our friction force, which is, well, not our friction force, our spring force, which is k delta L. And then it's going to be sine of theta, which is just going to be 3/5. So 3/5. Then if we move to this guy, it's going to be positive. So it's going to be plus mu s times by n. And then it's going to be the opposite side, which is going to be sine. So it's 3/5. And then minus our weight again. So minus mg. So now, leave all the n's on one side, add everything to the other side. Technically it would be subtracting, but they're already negative, you know. So add them to the other side. So then you get basically n 4/5 plus mu s, or write that a little bit better. Mu, oh, that was worse. Oh, if I could. Sure. We'll go with that one. So then this could be like that. And then this is going to equal, so add it to that side, add that to that side. So k delta L 3/5. And then positive, John, positive. So then it's mg, and then, so now we can pull out an n from both these. So then we get n parentheses 4/5 plus mu s. Why couldn't I do that earlier? 3/5, and that equals k delta L 3 over 5 plus mg, you know, same stuff over here. So now let's simplify it a little bit, you know, plug in stuff. So, and 4 over 5, or you know what, because I use decimal points in the calculator anyway. So 0.8, 0.8 plus 0.2 times by 0.6 equals, so now if we bust out our calculator for this part, so it's going to be 100 times by 0.1 times by 0.6 plus 2 times by 9.81. Whoa, I don't know if that was all that, but yeah. Okay, so then, yeah. So on the right hand side is 25.6. So 25.62. So now if we divide that by this part, we should get n in the end. So that's going to be 0.8 plus 0.2 times by 0.6. So then you get 27.84 or 85. So n in the end is 27.85. If I remember that correctly, yeah. That's going to be in newtons. I just always find it weird writing an n on this side and an n on this side too, but you know. Units, variable, you know, but yeah. Anyway, so now if we do the sum of the forces in the y direction, or I mean the x direction, that's going to be negative ma, you know, heading the accelerating in the negative direction, and then that's going to equal, so, or you know what, I'm going to make it positive, that way I don't have to multiply a negative on both sides. So this is the positive direction, positive direction. So if that's the positive direction, then this is going to be positive, this is going to be positive, this one's going to be negative though. So then we have, so n sine of theta, so sine is 3 over 5, and then plus k delta L, and then it's going to be the x component, which is going to be cosine, so that's 4 over 5, and then minus us times by n, and then it's going to be, or yeah, I'm going to have to erase this later, so we'll write it up here. So minus, no, we'll write it below. So minus us times by n, and then it's going to be the adjacent side, which is going to be cosine, so it's going to be 4 over 5. So in the end then, so it's mass times by L, 4 over 5, omega squared equals, and then just calculate this real quick. I can group this, and I'll probably just do that on the calculator then. So we have our normal force, so it's going to be second answer, and then it's going to be 0.6. 0.6. So I'm just pulling out an n from this term and this term and leaving this one alone. So it's going to be 0.6, and then minus, so mu s is 0.2 times by 0.8, and then plus, so we group those two, then we have 100 times by 0.1, and then times by 0.8. And then that should be this side in the end. So that's 20.25. So then basically in the end we're just going to go straight to omega f, and then we're going to do small. And so if we divide by all this to the other side, bring this over a little bit. So it's going to be parentheses 2 times by L is 0.4 times by 0.8. And then get the square root of that. We get omega small, which is 5.63. Yeah. 5.63. And then that's radians per second. Rad per second. Boom! Magic one again. So yeah, so I just cleaned it up and wrote our smaller answer over here. So now onto the larger omega, and that's going to be the scenario when the friction is going down the pipe. And then so if we broke it up into components, like the spring force, this is going to be theta. And so this is going to be mu. Ooh. I don't know why I can't draw mu's today. I don't know, that's good. Oh, that's super good. Well, anyways, so now if we do the sum of the forces again. So sorry if this is a little bit repetitive, you know, but practice makes perfect. So watch a lot of these, do a lot of them, you know, spend a lot of time. That's all. But yeah, so anyways, so in the y direction, it's going to equal 0, and that's going to be n cosine, so n 4/5, and then we have minus k delta L, and then it's going to be 3/5, because it's sine, and then it's going to be minus mu s n, and then this will be sine, so that's 3/5 again, and then it's going to be minus mg, so because that's the weight. So again, get all the n's on one side and all the other stuff on the other side. So then it's going to be n, and then that's going to be 4/5. And so since we have all the n's on one side, I'm going to just add these two. So just to save another step. So it's going to be minus, so in the parentheses it's going to be minus mu s times by 3/5. So, and then that's going to equal, and then, so we have to add this one and this one to the other side. So it's going to be k delta L 3/5 plus mg, and then so n, yeah, I guess I have to figure out what this is first, but yeah, so this is going to be 0.8 minus 0.2 times by 0.6. And so now if we bust out our calculator again for the thousandth time this time, it's going to be 100 times by 0.1, and then times by 0.6 plus 2 times by 9.81. So then you get 25.62. So 25.62. So in the end, then we find out that n equals, so divide that by 0.8 minus 0.2 times by 0.6, close parentheses, and then we get 37 point, what was that, 6.8. That's going to be newtons. Again, we get this awkward mess. And then so now if we do the sum of the forces in the x direction, again, I'm going to just say this is the positive direction, you know. So that's just going to be mass times acceleration, and that equals, and basically everything's going to be positive. So it's going to be n, yeah, or a better n. So it's going to be n, and there's going to be sine, which is 3/5, and then it's going to be plus K, delta L, and it's going to be sine again, so it's going to be 3 over 5. Or no, it's going to be cosine, so we have to do the x direction. So it's going to be 4 over 5. And then cosine again for that guy, so it's going to be plus for the friction. So plus mu s times by n, and then 4 over 5. So now it's going to be mass times by acceleration's that, so it's L 4 over 5 omega squared, and then that's going to equal, so now let's just get our calculator out. So this is the normal force, and then if we basically do second answer, and then it's going to be 0.6 plus 0.2, because we have to, if we combine these, 0.2, and then it's going to be times by 0.8, close parentheses, and this is going to be plus, and then 100 for the K, and then times by 0.1 for the delta L, times by 0.8, and then that should give us our basically the right hand side. So that's 36.63, yeah, 63, and then so omega in the end, so omega f large, so it should be bigger than this number and this number, I guess. So it's kind of cool that this one's going to be in the middle, you know. But yeah, so that's just going to be, bust out the calculator again, so divide by parentheses, so L is 0.4, or let's start off with the mass, be a little bit much smarter, so it's going to be 2 times by 0.4 times by 0.8, and then square root of that. Oh, get rid of that. So then you get 7.57, I believe. Yeah. Which is actually greater than both those. And 6.52 is in the middle. So that should be perfect then. So as you can see, the friction causes it to have a range for omega. But if there's no friction, then you get a specific value for omega. So I just like this problem because it's, it's kind of out there, and we also have to get this guy involved a little bit because this shows up a lot in just like engineering mechanics classes and just, also physics 1 mechanics classes. So, but yeah. So anyways, that's all I have for today, This is our answer. These are our other answers, and so yeah, so I hope to see you the next time.